Hello, today we're going to be talking about the energy of phase changes. So this is one type of phase diagram where we're looking at the temperature change as the energy is changed, or the heat energy is changed. You can also have phase change diagrams where we're looking at pressure versus temperature, but that's a different type of diagram. This is the one that we need to focus on. It was temperature versus heat absorbed. Okay, and you'll see it looks kind of like a staircase, or a weird looking staircase. Where the temperature is changing as heat is absorbed, that's when it is one specific state of matter. During a phase change, so when it's melting or boiling, the temperature stays constant, and that's really important. So in those areas where the temperature is constant, the heat that is being absorbed is being used to break the intermolecular forces. Whereas in the single state sections, the extra heat is being used to increase the speed of the particles, which is why you'll see an increase in temperature, because temperature is a change in, or is a measure of kinetic energy. So I'll say that again actually. Whenever the temperature is changing, the heat is being used to change the speed of the particles because it's changing the kinetic energy. If the temperature is not changing, the heat is being used to break the intermolecular forces and change the state. Now this one in particular is the phase diagram for water. I can tell because the melting temperature is 0 degrees Celsius and the boiling temperature is 100 degrees Celsius. When you're dealing with a phase diagram like this, when the temperature is changing, I can use Q equals empty delta T to find out the amount of heat that is involved in that process. You just need the mass, the specific heat capacity, and the change in temperature that's happening there. But for the sections where the temperature is not changing, I can't use this, because then my delta T would be 0 and I'd calculate a 0Q, but we know that's not true because heat is being absorbed. It's just not being used to change the temperature. So we're going to use a different equation for those sections. So during a phase change, we're going to call that the heat of fusion or the heat of vaporization. So fusion is just a fancy name for melting. And then vaporization, it could be boiling or evaporating, but it's changing from a liquid to a gas. So this is from solid to liquid. This is from liquid to gas. Now, if you were to add those together, you would get the heat of sublimation. But you won't see that on a phase change diagram typically because you want to go stepwise from solid liquid to gas. Sublimation is going directly from solid to gas. So if you add those together, you'll get the heat of sublimation. It's just you're not going to see that on the phase diagram. So we're using this delta H to indicate the enthalpy, but effectively it's the same as Q. It's just a very specific Q. Now, for fusion itself, it's going to be a positive value because going from a solid to a liquid is endothermic. But let's say I wanted to go in the reverse. I wanted to go from liquid to solid, so freezing. It will be the same value as the heat of fusion, just a negative sign, because it's exothermic. You have to get rid of some heat to get it to freeze. The same thing for heat of vaporization. Heat of vaporization is a positive value. It's endothermic to go from liquid to a gas. If I were to reverse that process, gas to liquid, that would be condensation. And it would just be the same value as the heat of vaporization, just negative because it's exothermic. So we don't have separate labels. We don't say like delta H freezing or delta H condensation. It's the same number. We're just going to change the sign when we're going in reverse. Now to calculate the delta H of fusion or vaporization, you just need to pay attention to the units. For the most part, it's given in kilojoules per mole. So if I want to know the kilojoules, all I have to do is multiply by the moles. So moles cancel. And that will give me my heat for that section. But occasionally they'll give it to you in kilojoules per gram or joules per gram. And so then you'll just multiply by the grams. So grams cancel and you'll get just the kilojoules for that area. You just pay attention to the unit. Just to make it really clear, let's go over those endothermic phase changes. Endothermic is when you go from a solid to a liquid to a gas, or a solid directly to a gas. You have to absorb energy to get it to go in any of those directions. The exothermic phase changes is going to be the reverse of those whenever you're going from a liquid to a solid, so freezing. If you're going from a gas to a liquid, condensation. If you're going from a gas directly to a solid, that's deposition. All of those are exothermic. You have to get rid of some of the energy to slow it down and change it to a different state. So just make sure you're really, really clear on the endothermic versus exothermic phase changes there. Okay, so let's put it all together. Let's say we have 18 grams of ice at 0 degrees Celsius. Okay, 18 grams of ice at 0 degrees Celsius. Let's calculate how much total heat energy will it take to change that 18 grams of solid ice to steam, water vapor, at, let's say, 120 degrees Celsius. You have to calculate each section separately because each state of matter is going to have a different specific heat capacity, and you're going to have different values for the heat of fusion and heat of vaporization for water. Now this one's specifically water, right? But you could have different phase changes. So I need to, since I'm melting it and then boiling it, I need to go in this direction, and I need to go, I need to first melt it, then increase the temperature of the liquid, then boil it, then increase the temperature of the gas. So I have 4 calculations I need to do. The first one, I need to take the 18 grams of ice and multiply it by my heat of fusion because it needs to melt. So in this one, they give it kilojoules per gram, so I'm going to multiply that by the 0.333 kilojoules per gram. And it will give me the 5.99 kilojoules total. The second section is when it's a liquid, and it's changing temperature, so I can use Q equals MC delta T. I have 18 grams. My specific heat as a liquid is 4.18. And my change in temperature for that section is from 0 to 100 degrees Celsius, so it's a 100 degrees Celsius change. That gives me 7524 joules, or 7.52 kilojoules. I'm going to go ahead and put everything in kilojoules to make it constant as we go through. The next section, I need to boil off the liquid, so I need to use the heat of vaporization. So I have 18 grams times the 40.7 kilojoules per gram. Notice that's much higher than the heat of fusion. That's because you have to break all of the intermolecular forces to get it to turn from a liquid into a gas. And I just need to multiply those two. The grams will cancel, and I will get 733 kilojoules. The last section, I need to go ahead and change the temperature of the gas, so I can use Q equals MC delta T. I have 18 grams. This time I want to use the heat capacity of the gas, so it's the 1.996. And the change in temperature there, I'm just trying to get it from 100 to 120. Because that's the arbitrary number that I picked, so we're going to change it to a gas at 120 degrees. So when we multiply that, we get 718.5 joules, or 719 kilojoules. So then to find the total energy that it took for that whole process, you're just going to add them together. So when you add those 4 together, you get 747 kilojoules. So that's how much energy it took to take 18 grams of solid ice and change it to steam at 120 degrees Celsius. It's a lot of kilojoules. Okay, let's look at another example, but this time let's look at, this one's mercury. So it has a different phase change diagram, and it has different melting and boiling points, different heats of fusion, different heat of vaporization. So given the heating curve for mercury, calculate the heat to freeze 100 grams of mercury at its melting point. So we just need to use this portion of the graph here. It's not changing temperature. Can't use Q equals MC delta T. So I just need to use that heat of fusion, which is the 2.3 kilojoules per mole. So I have 100 grams of mercury. I need to go ahead and change that into moles. So there's the molar mass of mercury is 200.59 grams. That way we have moles, because they gave it to us in moles here. And then from there, this one just says to calculate the heat. So I need to pay attention to the sign. And since we're freezing it, that's exothermic, right? So it's releasing the heat, and we're going backwards, right? So instead of 2.30 kilojoules per mole, it's negative 2.30 kilojoules per mole, because we're freezing. So the moles cancel. So I'm going to do 100 divided by the 200.59 times negative 2.3. So I get the heat for that process is negative 1.147 kilojoules, or 1.15 kilojoules with 3 sig figs. That's how much heat is involved in that process. You could also say 1.15 kilojoules released, if you say it that way. Okay, so this one didn't give you the heating curve, but it gives you all the information you need. Aluminum melts and freezes at 933 Kelvin. How much energy is required to freeze 2.5 moles of aluminum at 933 Kelvin? So if you're ever kind of confused, you can draw your own heating curve. Right? So solid, melting, liquid. We don't know, the boiling point, it doesn't tell us. So we just need this portion, and since it's at the melting point, we just need this flat part. We don't need to use Q equals MC delta T. But it is saying to freeze, so we're going to go backwards. And so instead of using this positive value, I need to use negative 10.9 kilojoules per mole. So I have 2.50 moles of aluminum, and we know to freeze it's negative 10.9 kilojoules per mole. Moles cancel. So I get negative 27.3 kilojoules for that process. So the heat for that process is negative 27.3, or you could say there's 27.3 kilojoules released to freeze it.